Oracle database and instance architecture. In this nugget, we're going to take a look at what's really going on behind the scenes with your Oracle database. For example, we'll take a look at the actual database, and then we'll talk about, well, what's the instance and what's the difference between the two. You'll be surprised at how often people misuse these two terms. We'll take a look at all the memory structures required to run your Oracle database, as well as the background processes and how these slightly differ on Unix and Linux versus Windows. Similar to background processes, we'll take a look at server processes, which are essentially fetching information for us. And then we'll take a look at physical structures. What are the actual data files that are doing the work for us? We have about 7 or 8 different types of files that we'll be working with. We also have logical storage structures. Logical storage structures are those which can be queried through Oracle, but they cannot be seen on the physical operating system level. So we'll take a look at how all of your database objects are organized. For example, where are your tables going? Well, we'll talk about table spaces and what all is contained inside of a table space. And then the last thing we'll take a look at is we're just going to put it all together and talk about what happens when the database starts up. We'll also take a look at what happens when someone issues a query. And so you'll get the big picture of what's really going on. So let's get started. What's an instance and what's a database? Well, an instance is just a collection of background processes and memory structures used to tap into a database. And a database is just a collection of files that contain your data. Now in Oracle, these files are usually going to end in the .dbf extension. And these are binary files, so if you try to open it up in a text editor, good luck reading it. Unless, of course, you're really good at reading binary. I haven't met anyone really good at that yet. Really, the only way to access the data in the database is to issue a SQL query. Okay, so here on our upper diagram, we've got an Oracle instance. ORCL is, in our case, just the unique identifier of our instance. Now your database has a unique identifier as well. That's the database name. And if you're in a situation where you've got one instance tapping into one database, most likely the instance in the database will have the same name. Now you can have a more complex scenario where you've got multiple instances tapping into one database. Here we have down here below. This is what we call a rack environment, or real application clusters. And the whole purpose of this is to have 24/7 uptime. So if in case one of your instances goes down, the others can take over. So notice how our different instances have unique names. If you're ever curious what those values are on a database, you can simply type in at your SQL prompt, show parameter db_name. That shows you the name of the database. You can also say show parameter instance name, just like that. This show parameter command, that just shows us what our initialization parameters are set to, and we have a whole nugget covering all those parameters. So what exactly are these background processes and memory structures? Well, I've drawn you a nice little diagram to show you. Let's look at our memory structures first. Right in this inner rectangle, we've got the System Global Area, otherwise known as the SGA. The SGA consists of a lot of different components, but really the only required components are the 3 down here in red. We've got the buffer cache, the log buffer, and the shared pool. The other memory areas are all optional up here, the stuff in green. So focusing in on the buffer cache first, the buffer cache is just an area of memory that stores data blocks. Okay, now everything is stored in blocks in Oracle, and we'll discuss exactly what a block is in a couple minutes. But basically, if you issue a SQL query and then you issue the same SQL query later, or a similar one that's accessing the same data blocks, instead of having to access that information from a file, it's actually grabbing it from cache. So it improves performance. When you make modifications to your data, that actually initially gets stored in the buffer cache, and then it eventually gets written to file. So you don't have this constant I/O activity going on. One of the biggest issues that we have with any database system is performance, and your goal is to have as little input-output or I/O activity as possible. Okay, so that's really the whole purpose of caches. Next, we have the log buffer. The log buffer is an area of memory that just saves changes made to the database, and eventually this will get written down to redo logs. The whole purpose of our redo logs is to perform recovery. Recovery is just the process of applying these redo logs to data files in case you had some corruption going on. So we'll talk more about recovery and how that works later. And then the shared pool is where parsed SQL statements get stored. So if you have SQL statements that are executed over and over again, they would get cached in that memory area, giving your applications better performance. The shared pool also stores data dictionary information. And well, what exactly is a data dictionary? Well, it's just a place where meta information about the database is stored. There's several hundreds of tables in the data dictionary describing what tables we have, what indexes we've got, what users we have, and so on. Let's hit on some of these optional memory areas. First of all, starting off with the Java pool, that's used obviously for Java. Oracle comes bundled with a Java runtime environment and some development tools. Then there's a streams pool. You're only going to use this if you're in a distributed database environment. In other words, if you've got multiple servers hosting a database. The large pool stores information about backup and restore activity as well as shared server information. Shared server simply means that we've got several clients sharing the same server process to grab information from the database. So we'll cover that in more detail in a little while. And the large pool also stores some other miscellaneous information, which we'll eventually get to. Let's talk about the keep pool. Now, things that you want to keep pegged in memory, such as lookup tables, are going to go there. And you can explicitly say, hey, I want this table to go in the keep pool. So it stays there as long as it can. Think of the recycle pool as being the opposite of the keep pool. If we need to do a full table scan, for example, we need to grab all the rows in a table, and we don't want it to clog up our main memory, our main buffer, then we can have this go to the recycle pool. And so if we happen to need this data, then it's there in the cache. However, it's not taking up space in our buffer cache. Before we talk about the 2K, 4K, 16K, and 32K buffers, I want to talk to you first of all about block size. Now in Oracle, you have a default block size for all of your objects. When Oracle is retrieving information or passing any information around, it's always going to be in block sizes. And when you install your database, you decide what your default block size is going to be. So here mine is 8K or 8192. Okay, 8 times 1024 is 8192. If I run a data warehousing environment where I'm dealing with really large rows, I probably would have made my default block size be 32K. For everyday operations, 8K is good. Once you define the default block size of your database, it's set in stone. You really can't change it. But what's really neat is starting with Oracle 9i, Oracle has allowed us to have multiple block sizes. So in addition to our default block size, we can have up to 4 other block sizes. So looking back at our diagram, the reason why we're missing the 8K buffer is because that's already accounted for right here. That's the 8K buffer cache. So when you're creating database objects, you can specifically say, hey, I want this table to belong to the 32K buffer or the 2K buffer. And so if you've got a table that uses that block size, it's going to use one of that buffer instead of the default buffer cache here. Let's check out our processes. Anything in a circle in this diagram represents a process. Now down below here, we've got checkpoint, database writer, log writer, archiver, process monitor, and system monitor. So let's start off with our database writer, DBW0. The reason why there's a number there is because we might have more than one process, DBW1, DBW2, and so on. Okay, so this process is just responsible for writing information from the buffer cache to the database file, and it does it in blocks. Remember, everything is done in blocks, not records. The database writer does not continually write blocks from the buffer cache to the database file. Instead, it writes it out, it flushes it out on a regular basis in intervals, or when the buffer cache becomes a certain percentage full. And next to the database writer, we've got our checkpoint process. Now, a checkpoint is going to occur whenever the database writer flushes the buffer cache out to disk. A checkpoint also occurs on a regular basis, defined by some initialization parameters, and also whenever redo logs become full and a redo log switch occurs. We'll talk about redo logs in just a moment. So all this checkpoint process does is it updates the data file headers. So everything in the database is synchronized. Next, we've got our log writer. That's writing log buffer data to the redo logs. Do you see how I just added another redo log there? The reason for that is that we need to always have at least 2 redo logs. Once one of them gets filled up, then the other will get written to. Once that's filled up, then it writes in a circular fashion back to the other one. Now, if we have archiving turned on, then before a redo log is overwritten, it's going to save that information to the archive log. Now, if you don't care about your data, then don't turn on archiving. For example, if you're in a test environment or a development environment, doesn't really matter, save the disk space. And once again, the only purpose of our redo logs is to perform recovery. Next to our log writer process, we have our archiving process. You can have more than one, so they'd be arc0, arc1, arc2, and so on. Notice there's not a star there because it's not a required process. If you have your archiving turned on, then that process will be there. We'll talk later where all these archived log files are going to go. Then we have PMON, or the process monitor. This is used for any of the user processes. If anything goes wrong, for example, if a session gets killed or it fails for some reason, then this PMON is going to come along and clean up any resources, clean up the cache. PMON is also going to start any server processes if they've failed. And then last but not least, we have SMON, which is the system monitor. It's going to perform instance recovery. So if you improperly shut your database down, like pulling out the plug without doing a shutdown statement, then when the database starts back up again, SMON is going to go ahead and clean things up for you. Now, as far as these background processes go, these are the main ones. These are the more common ones. There are some additional ones dealing with advanced queuing and streaming, but we won't get into that quite yet. I mentioned earlier that there are differences between Windows versus Unix and Linux when it comes to processes. If you're on a Windows system and you want to see my Oracle processes up and running, go ahead and hit Control-Alt-Delete to bring up this nice Windows Task Manager. And make sure you go to the Processes tab. You can sort the image name by an alphabetical order, and Oracle.exe is going to be one process that has multiple threads dealing with all the processes. Now, if you're on Unix or Linux, then issuing the ps-ef, pipe that to grep Oracle, that's going to list all of the processes that are owned by Oracle. So you're going to see multiple processes. You'll see one for SMON, PMON, log writer, database writer, and so on. Okay, let's talk about server processes. They're right up here. A server process is responsible for grabbing the information from the database. So the server process is going to be on the actual machine that the database is on. And so it can tap into the data files and grab what it needs, and it also puts that information into the buffer cache. Okay, so I'm just going to put a little dotted line here just to show you this side is the server, and now a user process is going to connect to a server process. Let me give you an example. If you're logging into SQL Plus, Your SQL Plus program is a user process, and that's going to connect to a server process, which in turn is going to grab your data for you and return it back to you. Now, all these server processes have their own separate little area of memory called the PGA. It doesn't stand for Pro Golf Association. It's actually the Program Global Area. And that PGA memory area just contains information about the session, such as variables and cursor state information. For example, the data coming back to the user. So let's say we've got 15 users that are trying to tap into the database with different programs. We might have several using SQL Plus. We might have a few using Toad. There might be a couple using a Java program or a Perl program. All of those are going to be aligned with the user process. Okay, there will be a user process for each one of those programs. And then, so if we have 15 users, we're going to have 15 server processes. Now, what I just described to you is what we call a dedicated server environment. That's the default installation for Oracle. There's another type of configuration called a shared server configuration. In previous versions of Oracle, shared server was otherwise known as MTS, or multi-threaded server. We will cover all the details about shared server architecture in another nugget. Let's talk about the physical structures of your database. Now, the physical structures are those that are real files that you can see on the OS level. Well, you're definitely going to have database files. The naming convention is to have them end in .dbf. These are binary files, so if you try to open them up with the text editor, you will not be able to read them. If you want to see what data files you have in your database, you can query a table called, it's actually a view, DBA data files. Okay, so the column in there is file name, and there's a column for bytes. I'm just dividing by 1024 twice so I can put this in megabytes. It's just easier to read. Okay, so let's execute this. I've got a really small database. On a live production system, it's not unusual to see files that are 5 or 6 gigabytes in size. I want you to pay attention to the naming convention. So here we've got our base directory of Oracle product 10.2.0, and then underneath that you'll have Aura data, and then the name of your instance, and then the data file. That's a pretty strong naming convention. Do not veer from that. So on a particular machine, you might have more than one database. And so remember, each database is going to have its own particular name. And so then you can go through your operating system and tell just by the naming convention what it belongs to. And you can also find out when a file was created by querying the $$ data file view. Okay, so select name, creation time from $$ data file, and there we go. Let's look at our redo log files. Where do we find those? Well, we can query $$ log file to find out where they are. And once again, look, it's under your Oracle Home, Aura data, the name of your database, and then the name of the redo log. Now, each redo log file will belong to a group, and it's a good idea to have more than one redo log file per group for redundancy in case one of them fails, because those redo log files are very important. Remember what they do? They're used for instance recovery and other types of recovery. Let's look at another view called $$ log. This shows us information about our log group. So once again, we have group numbers 1, 2, and 3. Then we have the sequence number. The sequence number is a unique identifier. Notice that it is incremented by 1 every time. And once our sequence number 10 redo log group is filled up, notice that this is the current one that's being written to right now. Once that's filled up, then the next one will be group number 1, and then its sequence number will be 11, and so on. So it does get written to in a circular fashion. Then we can see the size in bytes of each of our groups. You always want to have the members in a group be the same size, and you also want to have each of the groups be the same size. Then this column for archive just tells us yes or no. Has this been archived to an archive log? So our current one has not been archived yet. The status of inactive simply means that this redo log group will not be necessary if we need to do instance recovery. So at any given point, there's always going to be exactly one group that's going to be the current redo log group that's getting written to. The way I have my database set up right now, I have 3 redo log groups, and there's only one member in each group. Now ideally, I'd like to have more than one member in each group and have some mirroring going on. In other words, have those additional members be on a different disk in case we have media failure. So this is what we would like to have. Okay, so let me show you how to do that. So we go ahead and alter database, add log file member, give the full path of where that file is going to be. The directory already has to exist, otherwise you'll get an error. On Windows it's not case sensitive, on Unix and Linux it is. And then you specify which group you're adding it to. Good, database altered. We'll do the same thing with group 2 and to group 3. So now I reissue this statement. We're looking at our group members and their status. Now these new files here are invalid. It just means that Oracle can't access it now. What it means is we need to clear the log files. We need to make it ready for Oracle. One way of clearing the log files is to issue the alter system switch log file. What that does is it makes the current log file now be the next log file. So it clears it out. And so I issued this statement 3 times because we've got 3 redo log groups. If you want to add a completely new redo log group, then you're going to once again alter database, add log file. You can also explicitly mention a group number. If you don't, then it will just go to the next group available group number. And then a comma separated list of files. You also have to specify the size of this group. Now we didn't have to do that earlier because there was already a size mentioned for the original log file in that group. And sometimes it takes a while. There we go. And you can even drop groups just like this. So since these log files are always written to in a circular fashion, you always have to have at least 2 groups. So in our nugget covering recovery, we're going to talk more about these redo log files and what role they play in recovery. You're also going to have undo table spaces, which are used for rolling back information in case you deleted or updated some data you didn't want to. Well, that undo table space will have corresponding undo data files, and those will have a DBF extension, so it's treated essentially like a data file. When you're starting up the database, you're going to have either a server parameter file, we call that an SP file, or you'll have an old style initialization file. Now, the SP file came about in Oracle 9i, but in 9i and 10g, you have your choice of using one or the other. And we have a whole nugget discussing what the differences are between those. I really do prefer using SP files. So let's take a look at where ours is. If you type in show parameter SP file, it's going to show you the full path of where your server parameter file is. Now, if you're using the old style initialization file, then this will show up as blank, and you'll have to look under the Oracle Home directory for the initialization files. Let me show you where that might be. We look under the DBS directory, and what Oracle does upon startup is it first of all looks for a file called spfile, then the Oracle SID.ora. If that file doesn't exist, then it looks for spfile.ora. If that doesn't exist, then it looks for init, and then the orcl.ora. And if that doesn't exist, then your instance doesn't start up and you'll get a nice little error message. Just to show you another example, let's assume that our Oracle SID is XYZ. So upon startup, Oracle looks in that directory for spfile xyz.ora. Oh, it's not there. Okay, go on to the next one. spfile.ora, not there. Ah, maybe we have an init xyz.ora. It will use that one. One of my favorite files is the alert log. That tells us about major events on the database. For example, when we start up, when we shut down, when log switches occur, when we accidentally fat finger a command, all that evidence goes in the alert log. Now on a more fine-grained level, we have trace files, and that's used on the session level if somebody did something wrong within a session. All those files are going to be in dump directories. Let me show you where those are. Background dump dest is where our alert log is going to be. So make a note of where this is. So here are all the files in that directory. See my alert orcl.log. That orcl, that's always going to be the SID. That alert log is a text file, so let's go ahead and open it up. These can get really, really large. I make it a practice to back it up to a file every 24 hours on really active databases. I can make naming conventions like have the date in the data file name. Notice also that I'm at the end of this alert log, and it shows us all the activity that we did on our redo logs. Control files, they have a .ctl extension. These are the files that are read by the instance when the database is starting up or when it's getting into the mount mode, and we'll talk about the different modes in another nugget. The control files contain information about the physical structure of the database. For example, where the different data files are, where the redo log files are. So when your database is trying to start up and the information in the control files does not correspond to the actual structure, physical structure on the OS level, then you've got a problem and your database is not going to open up. Let's look at our data dictionary view called $control file. If you do select name from that, it shows us where our control files are. Now, the optimal situation is where you have 3 control files at least on different disks. Now, I didn't do that on my machine because I only have 1 disk, but I am multiplexing it. Just multiplexing means you've got different copies. These control files are exact copies of each other. They have the same size, and we just have copies in case one of them fails. Now, if we've got media failure for some reason on one of the disks, then Oracle will eventually come to a screeching halt and let you know that there's a problem with the control file, and it will tell you which one is the problem. And then at that point, you would copy the good control file to the bad control file and figure out what in the world is wrong with your media and get it fixed. And then last we have backup files. Now that's just a conglomeration of things that you want to save in case everything gets hosed on your system. Oftentimes, if you've got a lot of data files, you might tar up those backup files. You can also compress them, and we'll talk more about backup and recovery in another nugget. The logical structures. How is our data logically organized in the table space? Now, when we talk about logical structures, we're talking about structures that can only be queried from the database. We can dig into our data dictionary and find out all sorts of interesting information. Let's pay attention to the stuff in blue first of all. The largest logical storage structure is what we call a table space. Every single database object is going to reside inside of a table space. Now there's 2 special table spaces that are going to exist on every single database, at least 10G database, and that is the system table space and the sysaux table space. Now the system table space has been around forever, since the very beginning of Oracle, and this is used for data dictionary and metadata information. For example, it stores information about the structure of your whole database. And then there's the sysaux table space used for auxiliary purpose. Now in previous versions of Oracle, in 9i and earlier, we pretty much just combined sysaux and system all into the system table space. Now a really good thing to do as a DBA is to make sure that your regular users do not store their objects in the system table space or the sysaux table space, because those are supposed to be reserved for special purposes. Typically you'll have a users table space. Really you can call your table spaces anything you want to. You can have hundreds of table spaces. Just try to organize your data into logical units, into logical table spaces. You're also going to have an undo table space. That's going to be used for storing the before image information about your data. So in case you need to perform a rollback, it's there. The temp table space is used for sorting data in case we don't have enough memory to do the sort. Now performing sorts on disk is a really expensive operation. Ultimately you do want to have enough memory to perform your sorts, but it's there just in case. Like I mentioned, every single object in the database will be contained inside of a table space, and only inside of one table space, unless you're performing partitioning. Then those different partitions can go in different table spaces. Okay, so let's look at this users table space. Here we've got a person table segment. So a segment is the next smallest logical unit. Looks like I also have an emp table segment. If my person has a primary key, well, we can have index segments as well. We can have table segments, index segments, temporary segments. It is possible for temporary segments to be not only in the temporary table space, but also in regular table spaces. For example, if you're rebuilding an index. We'll talk more about that later in our index nugget. Now let's say that you own 100 different tables in your schema. All of the tables in your schema do not have to belong inside of the same table space. They can be scattered among these different table spaces. So when you create a table or an index or any of those objects, it will initially be given a chunk of space called a segment. And then once that data gets filled up in the segment, Oracle's going to allocate another chunk of area, and we call that an extent. Okay, so I'm going to draw a little rectangle here. Okay, so here we have our person table extent. Notice that it's not connected to this segment because there might be gaps. There might be some fragmentation going on. Once this extent gets filled up, then of course Oracle will allocate more and more extents. And you can specify a max number of extents if you want to. You can specify information such as, well, how large is my original segment going to be? How large is my next extent going to be? And so on. The definition of an extent is several contiguous database blocks. Okay, so I'm putting lines here to represent the different database blocks. So a database block is the smallest logical unit. Now, a database block does not map exactly to an operating system block, but it will be a multiple of the OS block size. In a later segment, I'm going to show you how to manage your table spaces, how to create one, how to modify it, how to drop it, even how to create the objects with specific table space parameters. Let's put this all together now. Let's assume that I want to tap into a database and I'm using SQL+. So that's my user process. It's the client. So I'm right over here. Let's also assume that I'm in a dedicated server environment. So each user process has its own server process. So we'll communicate here with the server process. By the way, that server process was started up by the pmon process. And my server process has its own program global area to store variables. So then I issue a statement, select something from something. It doesn't really matter what it is. That server process is going to attempt to grab the information from the buffer cache. If it can't find what it needs there, then it will actually read the data from the database file down here and then store that data in the buffer cache and return it back to the user process. If I performed any kind of update activity, such as inserting records, updating records, then any changes will be noted in the log buffer, and then during a checkpoint, that data will be written to the redo log by the log writer. If we have our archiving turned on, I'll show you later how to turn it on, then once one of these redo log files gets filled up, it's going to then write to a new archive log. You can end up with quite a few archive logs. For all of those statements, whether that's select, insert, update, delete, whatever, all of those statements are getting parsed, and the hash value, it's a unique identifier for the command, will be stored in the shared pool. So basically, you're caching your commands. So that's really what's going on. Well, I hope this has been informative for you, and I'd like to thank you for viewing.